After a long wait, today is the day we will finally be assembling the CPU itself. Welcome back everybody to the series in which I show you how to build a CPU in Scrap Mechanic using logic gates. You may recognize this from several videos ago. This is the code spooler that was built long ago. And if you don't know what that is, let me explain. A spooler is the fetch part of the CPU cycle. The spoon that feeds the food or the code to the processor to do. Attached to the spooler is the ROM, a read-only memory that holds the code and is similar to a bowl which holds the food. In this case, the programmer is the brain, deciding in what order to eat the food available. Now, this is off topic, but I thought it was interesting. A simple way to explain multi-threading would be like having two hands instead of one feeding the processor. Again, what goes into each spoon needs to be specified by the developer, but it saves time in the code by immediately having more code ready to be processed. Now, we should get back to building. Now, I'm going to recap exactly what the spooler does. To start the loop, the yellow switch must first be turned on, and then the green button. That will tell it to do one operation. It will send out this currently requested address to the ROM, and upon it being placed down, will be set to 0, as it is here, and then it will get the information and store that number back here. Now, at this point, it will send the code to be processed by the CPU, putting the food into the mouth to chew on it, so to speak. Now, this part is what we'll be discussing in this video, how the CPU does the processing. This right here is the interface between the spooler and the CPU itself. Since the code the CPU uses is 16-bit, we have 16 logic gates here, which are separated into a 4 and 2 6s. To the left, we have this pin here that tells the CPU the information is here to process. And to the right of it, we have this pin here, which will tell it that it is done processing the information it was given. Next to that are 9 pins, which handle jumps. That will be discussed later. The reason these command pins here are separated into 3 chunks is this. The first 4 are for specifying what command is being done, and the other 12, the 2 chunks, are the parameters. Sometimes they're used as one large number and a chunk of 12, but sometimes, like in if statements, you need 2 things, and it's used as separate parameters. So, to start off, we need to decode these 4 bits here to know what command is being run. And to do that, we'll need a binary decoder. I happen to have one saved here. This is the one I use all the time, by the way. So after spawning that in, I'm going to need to connect this up. And the 4 bits will line up conveniently with the 4 inputs. Now to verify that I have it going the same way, you can see that it is correct now. So now I'll connect it up on the side of the processor. Now, this means that anytime we send in a command, it'll go through these 4 pins and be decoded into one of the 16 outputs. But to regulate the CPU, we're going to need to wire the go pin, which is this one here, onto a pulse regulator in order to standardize the amount of time each command is made available. So let me get that. This was also discussed in a previous video. So wire it up like that. And then I need to hook it into each of the outputs. This is to standardize the amount of time that the code is accessible. Why, you may ask? Especially, you may be asking, because there's already one on this side. Well, even though it's doing the same thing on the spooler end, that is because on this side, it needs to regulate it because it takes so long to decode the number, and it needs to be available for that amount of time. The one on the spooler side only regulates how long the command is sent over, not how long the operations are, which is what this one does, because of the delays and the amount of time it takes to decode. It does that because you might get the wrong output otherwise, and this way you only get one output per your input. But in order to get the amount of time correct, we need to realize how much time is being given over here. 9 ticks. So I think it would be reasonable to set this one to something like 6. Now if we write into our code over here some random command, we should see that we only get one output. But that was really quick. Let me put a button over here so I can see that better. And there we go. That's the 2 outputs I was talking about. That's something that needs fixed a lot of times. It does take a lot of trial and error to get this stuff right. But as you just saw there, putting this one on 4 gives it a lot more time. In fact, I like to have pretty long operations, so set that one to maybe half a second, maybe 15 on this one. See if it will do it correctly. And now it does. Now we can continue. The first operation we're going to implement is called, quite intuitively or counterintuitively, no operation. In this operation, the CPU does nothing. This is specified by operation number 0 in this instruction set. So when these 4 bits read all zeros, it'll be decoded into 0. And then this will go to activate the circuitry for no operation or no op. Now the output from the binary decoder for no op is connected right back into the done pin, which should be an OR gate, by the way, because there's no processing that's actually doing here. It literally does nothing. Now, why have a CPU where one of the operations is nothing? Quite stupid, right? Yeah. Well, the real reason is that it takes time to do it. Time to get the command, send it over, and get it back and get the next one, even though it has no processing circuitry. Also, having nothing written on your ROM, such as here, given the fact that it's blank, would mean that it will do nothing for that entire time, instead of having it do a different command, such as, I don't know, add 1 to your number. It would throw off your information. No op is also useful for system interrupts, which will be discussed in another video. This is because a lot of my CPUs I build can't have a loop where a line jumps back to itself over and over. So instead I have no operation is where it jumps to, and then it goes to the jump command in a loop. So if I wipe this command that we wrote earlier, we should now see it, because there's nothing written, go into a loop of nothing. And there we go. As shown here, that is now working. Before we get into the next operation we're going to add, we need to add the most important part of a CPU, the register, which I'll spawn in now. The register is also called a cache sometimes, but it's basically where the number is being currently processed by the CPU and where it stores that number. Every CPU has at least one. There are many uses for having 2, 4, or even more, and modern CPUs have a lot of these. However, since this is a simple scrap mechanic CPU with a limited instruction set, we're going to be keeping it simple. So now I'm going to attach it down. I'll just pick a random spot. About here seems good. Also, since this uses logic bits and it flashes upon being spawned in, I'm going to also place in a black circuit to reset it automatically. other storage technologies and real life stuff does not use these. Now that we have the register, how do we get numbers into it? Well, you can move them in from RAM. We just spawn this in, and the RAM's empty, hypothetically, because we don't actually have RAM yet. We could pull it in from a hard drive, but we don't have expansion card access. This leaves one final option, which is, in my experience, most commonly used. Set basically sets the register it is targeting to the number held in the parameters. This is one of the use cases where both parameters are joined together as one of 12 bits. But 12 bits? This looks like 16 to me. Well, I argue, think about it. When do you really need to use all 16 bits? When you can't pull it in from somewhere else like a hard drive. Very rarely will I actually use numbers that high. And for the problem use cases of set, such as resetting a register back to 0, not being able to use the first 4 bits is really not a problem. Now, to include the command to set, we need to have a set of AND gates behind it to allow the parameter in. Only the 12 bits. Now, we need to be able to have an output from our command. We have 0 on no op, and now 1 is going to be for set. Now we need to connect it to these 12, which will only allow the parameter information through once the command is run. And then the parameters need to be connected up to these, each their respective location. I'm just going to mark that I already did these. So, now that we have that, we need to have it actually go into the register. And this pin here needs to allow that information into the register. Now, we need to write the command to tell the CPU to, let's say, set the register to 1. Since it's on command number 1, we write down a 1. Let's say, set it to 1, the 12-bit number I discussed earlier, which is labeled here because the yellow means it's where you're writing the command, and then each parameter is seen here. Now, if you're building a CPU with multiple registers, you're probably going to want multiple set commands, one for each register. But in this case, we're just going to have the 1. So, let's send the command over. And that is a common issue, which is remedied by adding some delay. Start with 1. Interesting that that didn't work either. Let me see if I can't get an idea of what's happening. Pretty sure it'll work now. And look, now we have 1 in the register. But after that, we need to tell the CPU that it's ready for the next operation. So we take that same output and wire it into the done pin, meaning that it's ready for the next operation. So, the way this code currently reads is that it'll set the register to 1, and then it'll do nothing. Let's see that in action. And there you go. But having solely one number storage to work with is very limiting. We need access to a large set of numbers, which is what RAM is for. Now, to communicate with RAM, you're going to need RAM pins. Both these things are talked about in the RAM video I made some time ago. should check it out. It's linked in the iCards. But for RAM communications, there are two commands. The first is move, which will move your register data to the RAM and the address you specify. That's the first one we're going to be doing. Written out, it looks like this. Move being command number 2 in binary. We actually have 3, remember, no operation. And then the first parameter, ignore that it's separated here, it's still one number. We're going to tell it to write the register information to, say, address 3 of the RAM. Now, if we had multiple registers, in the second parameter is where you would specify what register it's coming from. But now that we have that, we need to get it actually made. So we have no op done. Actually, yeah, leave that one unpainted. We have set done. Now we need move. So coming out of move, we're going to need yet another set of pins coming out of the register. So now that we have that, we need to have the circuitry be activated when it's decoded. So we take that out of the decoding, which will decode when that number is present. Next, since we only have one register, we're going to need to copy over one of the parameters, which will be this first one, just like this. And to see that it actually works, I'm going to add a temporary button here, which will do the same thing as the green button on the front. And when pressed, you see that it does activate. But we have to only activate when the command is sent over. So we need to connect this to the other gates we just placed. So now that it's connected up, we should only see that this parameter and the registered data can be activated when this logic gate is activated, and that one will only activate when the command is sent through. So, there we go. Just want to see that again. Alright, perfect. Now we need to wire these up into our actual RAM port here. Need to make sure that the rightmost digit of the number will be still the rightmost digit of the number, so that you actually write to the correct information. And then we need to connect the register output to the data in for the RAM. So now that we have this command connected up to the RAM port, only now can we see if it actually works. Now the way this command reads out is that we're moving the registered data to address 3 in the RAM. Let's see if we get that. And this is address 3. There it is. But it's important to see, did it overwrite any of the other data? Doesn't look like it. And it didn't. That means we now have a working move command. So, to finish it off, we'd send it right back out to the output, telling it that it's done. Now, the next command, which is going to be binary number 3, does the opposite thing with the same parameters. It will take the specified RAM address's information and overwrite the register to that information. It does this by taking the output of the binary decoder, 3, and having that go to AND gates for the parameters, just like move did, and then it will go to the RAM pins. Then it will wait, and it will write that number that it gets to the register. There is delay involved. Now I'm going to build it. Take the next output from the decoder, which would be number 4 here. It's the 4th command we've done today. Wire it up. Replace my temporary button so it's out of the way. Wire this up so that the parameter it's going to copy is only activated once the command goes. And then I need to actually copy the parameter over. Just checking that the parameter, yep, parameter 1 is copied over, the exact same. And when we press the go button, the green button, well, this one isn't green, it does the same thing though. Should, yep, 3 is only outputted when we get that number. Next, we need to add a line of 16, which will have connection from the output of the RAM.
If the earth is round, how come the ball ain't going nowhere?
Nope.
So now that is hooked up, we need to send over our address pins, which is going to be coming from the parameter data. Now, this is important. Your RAM port should always be OR gates. It wasn't earlier. I changed that between clips. So now that all 6 are hooked up, we should press the button. It should send over the number we're requesting, which, if you recall, is 3. And then it should take a tiny fraction of a second, and we should get that number from number 3, which is 1. We sent over it earlier. And it should come across there into these pins. We haven't sent it to the registry yet, but that's what we should be looking at. And there it goes. Now, there's always a bit of delay involved. Let's call it 7 ticks. And those 7 ticks is how long it's going to wait to actually write the data over for it to decode and send out the right information. So by connecting this timer up, it will only write the correct information to the register. So to double check, let's make sure that that correct number will still appear. And it does. So, since we're going to need to test if the register will write it, we need to wipe the register with a handy button here. And then put that line of 16 back into the register, just like it did with the set command. And now we need to hook up this timer to this pin here. Now, upon pressing this button, which will send in this command, we should see it, get the information from RAM address 3, and put it into the register. And there we go. Last thing we need to do is we need to tell it that we're all done, ready for the next command. While conditional jumps, also known as if statements, won't be covered in today's video, simple jumps will be. This is useful in many circumstances, namely when you have a system interrupt. How it works is by taking the binary decoded output and the parameters, then wiring them back over the jump pins on the CPU spooler interface, and then it'll send the done command to tell it that it's done, telling it what address it needs to go to now. Now I'm going to build it. So I need to first check, and I'm going to color this pin, because this is the go pin for that, and these 8 are the addresses telling it to do. So how I'm going to start is the same as always. I'm going to take the next output in the decoder, which will mean for the next instruction, which is 4 in binary. Let's say we want to jump to a line in the code number 15, which I have it handily labeled, but at the moment it won't be doing anything. Merely just to show that it actually does here. I'm going to color code it. When this output is given, which means command 4 has been sent, we need to copy over the last 8 digits of the parameters, which includes the entirety of the second parameter and 2 bits of the first parameter. Now it's a bit unnecessary because everything else is 6-bit as far as addresses and stuff, but if you need that leeway, you'll appreciate it. I also need to verify which digit is 1, and it looks to be that it's the rightmost is the first digit. So that means we need to mirror it as it goes over this way. And then we need to send over that, hey, here's the number you're supposed to jump to. So when we press that button, we should see this over here turn into the number 15, which upon it sending the done command, it'll ask for the information from line 15, and then it will carry on. So let's have a look. And there's a common issue right there. What we need to do is change the amount of delay this has, which, if you didn't guess it already, we need to have a pulse regulator, and that will go between this being the binary decoded output and telling it that the number is here. I'd say 2 will work. And it didn't. See, the main thing about building CPUs is that your data doesn't always line up. Again, didn't work. So what I think I'm going to have to do is I think I'm going to have to add some delay between when the number is sent out and when the go pin for that goes. By building it like this, I can minutely adjust the delay between the two. So out of curiosity, I'm going to see if that fixed it in itself. And no, it didn't. See if 2 ticks of delay is plenty. And there we go. And then after that, I'm going to want a bit of delay, because this one takes quite a bit of time, say quarters of a second, before it says that it's done. So what this code should do is it should say, hey, jump to line 15, and it will, and it'll just continue on. So we reset it with the red button, and we start up the loop.
Some time later.
And now we can see that it is working. So, now that it's working, I'll demonstrate it again. What this code will do is it will jump to line 15, and then it'll do whatever line 15 says. So, right off the bat, jumps to line 15, then goes 16, 17, and so on. All of which are telling it to do nothing. There are many more operations that can be added to CPUs. And on this small of a scale, it is very important that you only choose the ones you need for the thing you're trying to do. The operations discussed in this video are very general, and you'll need them in most cases. Now, if you watch this far, you probably want to know more about this. And the easiest way to have that happen is by subscribing. I would appreciate it. And only 16.5% of viewers are subscribed. It shows that you want more of this content and that I should continue making CPU videos. Stay tuned for more episodes on this and more cool CPU related things within scrap mechanic. See you next time. The RAM port has different sections. We have